All right, welcome everyone. Have you ever stopped to think about how your GPS just knows the fastest way to get you somewhere? Or how Netflix is freakishly good at recommending your next binge watch? Well, that's not magic, it's algorithms. And today, we're going to open up what I like to call the programmer's toolkit to get a handle on the fundamental tools that make all that incredible technology possible. So let's get that lid open and dive right in.
So, first things first, the most fundamental tool in our entire kit is the algorithm itself. You can think of it as the blueprint, right? Before a carpenter can even think about building a chair, they need a plan. For us as programmers, that plan, that detailed step-by-step guide to solving a problem, well, that's our algorithm.
Now, this is the formal definition, straight from the classic textbook, Introduction to Algorithms. It sounds a little dense, I know, but let's just break it down. It's really just a precise recipe. Your input is like the ingredients. The procedure is the list of instructions. Mix this, heat that, and the output, that's your finished meal. So all an algorithm is a clear, unambiguous, step-by-step guide for getting from a problem to a solution. Okay, so if algorithms are our blueprints, our plans, what are we building with? What are our raw materials? Well, it's data. And just like any good workshop, you can't get anything done if your materials are just thrown in a big messy pile. You've got to organize them. And that is where data structures come into play. These are our storage containers. They're the shelves, the bins, the organizers in our toolkit. They give us specific, structured ways to hold on to our data so that our algorithms can find it and work with it without wasting time. To make this really concrete, let's talk about one of the most basic data structures out there, the array. And, the best analogy for an array is probably sitting in your refrigerator right this second. It's an egg carton. This analogy is perfect because it lays out the core ideas so clearly. The carton itself, that's the array, our container. Each little cup where an egg goes has a specific numbered spot, right? That's what we call an index. And the egg itself, the thing you're storing, that's the actual piece of data, which we call an element. It's that simple, a fixed number of ordered slots to hold our stuff. But of course, any good toolkit needs more than just one kind of box. We've got other containers too, like stacks and queues. A stack is just like a stack of cafeteria plates. The last plate you put on top is going to be the first one you grab. We call that last in, first out, or LIFO. A queue, on the other hand, is just what it sounds like. It's a line. The first person who gets in line is the first person who gets helped. First in, first out, or FIFO. Easy enough. And this, right here, this brings us to one of the most important questions a programmer ever has to ask themselves. We've got all these different ways to store our data. So which one is the best? And the answer is, well, there isn't one. There is no single best tool. The absolute most critical skill you can develop as a programmer is understanding trade-offs. I mean, you wouldn't use a hammer to drive in a screw, right? It's all about picking the right tool for the specific job you're trying to do. Every single tool has times when it's the perfect choice and times when it's not so great. So to really understand those trade-offs, we need a way to measure them. In the world of computers, the things we have in limited supply are time and memory. So we need a way to look at our tools, our algorithms, and figure out how efficient they are. How much time and memory are they going to chew up? Okay, the main way we do this is with something called time complexity. Now, I know that sounds super technical and intimidating, but don't worry, it's actually a pretty simple idea. All it is a way to talk about how an algorithm's runtime changes as we throw more and more data at it. Does it stay zippy and fast, or does it totally grind to a halt when you ask it to handle a million things instead of just 10? That's all time complexity is. And here are some of the common ratings kind of sorted from fastest to slowest. Let's just touch on a few. Up at the top, constant time. That's the dream. It means it takes the same amount of time no matter how huge the input gets. Then you have linear time, which is super common. If you double the data, it takes about double the time. Totally fine for most things. But way down at the bottom, you've got exponential. And that, my friends, is the danger zone. An algorithm like that can have its runtime just explode with even a small increase in data. The difference between the top and bottom of this list is literally the difference between an app that feels instant and one that might take, a few centuries to finish. All right, let's zoom out for a second. Beyond just these individual tools, programmers have bigger, more general strategies for tackling problems. Think of them as blueprints. These are the high-level game plans that help us structure our solutions. So let's look at two classic blueprints here, the greedy approach versus dynamic programming. A greedy algorithm is, well, it's greedy. At every single step, it makes the choice that looks best for right now, and it just kind of hopes that all those little right now choices will add up to a great final answer. Dynamic programming, on the other hand, is way more careful. It breaks the whole problem down into tiny little pieces, solves each one, and then, and this is the key part, it saves that answer so it never has to solve that same little piece again. It's that classic trade-off, right? Do you want something that's fast and simple, but maybe isn't the absolute best solution? Or do you need the guaranteed perfect answer, even if it takes more work up front? And listen, this whole idea of trade-offs, it isn't just for the basic stuff. This principle applies all the way up the ladder to some of the most complex, most specialized tools in the entire programming world, as you're about to see. Just take a look at this. Here we're comparing two very advanced data structures, two kinds of self-balancing trees. The AVL tree is super strict about staying balanced, which makes searching for data incredibly fast. But all that work to stay perfectly balanced means adding or removing data can be a bit slow. A red-black tree is a little more relaxed about its balance. That makes searching a tiny bit slower, but it makes adding and deleting data way faster. So which one's better? Well, it depends. If your app is doing tons of searching but the data doesn't change much, maybe the AVL tree is your winner. If your data is constantly changing, the red-black tree is probably the better bet. See, it's always about the trade-offs. So, we've opened the toolkit, we've looked at some of the tools, we've talked about the core principle of choosing the right one for the job. But why does any of this really matter? Why should you spend your time on this? I think this quote from the book on the subject really says it all. You know, it's one thing to just write some code that kind of works, but it's a whole other ballgame to actually engineer a solution that's truly efficient and solid. This knowledge, this is what makes that difference. Because knowing which tool to pull out of the toolkit, and more importantly, why you're choosing it, that's what lets you build software that isn't just correct, but is also fast, elegant, and can handle a massive scale. It really is the difference between building a rickety backyard shed and engineering a skyscraper. This knowledge is your foundation. So, we've laid out the first few tools on your workbench. You've got the blueprints, the containers, and the measuring tape. You now have the fundamentals. So the only question left is, now that your toolkit has its first few pieces, what are you going to build?